Okay, Chemistry 3202 course overview review. All right, this is a big lesson here. This is the meat of the section, I guess. There's always going to be a long answer question on this section. So Unit 2, Section 2, Lesson 4, Ka and Kb calculations. This is dealt with on various pages of your textbook, page 587 to 592 there. And there's a whole bunch of questions that relate to this, so you can check some of these out. Check them out with your tutor, your free online tutor, or you can drop me a line at the discussion posting and I can try and do a couple of these for you in the next session. Here we go. Okay, here are the outcomes for this lesson. In this particular question, we want to be able to, or in this section, we want to be able to calculate pH of various different acids or bases, or we want to be able to calculate K values or things like that. So there's a whole bunch of different calculations that pertain to this section. The very first thing we're going to do here is calculations pertaining to percent ionization. Now, one of the things about percent ionization is that these values can only be used for acid concentrations where the initial concentration is 0.1 mole per liter. There's a note on the bottom of your acid-base table. If you go check that out, you'll see that the percent reaction values, or the percent ionizations, are based on the idea that the initial concentration has to be 0.1 mole per liter. If there's any other concentration that we have, then we cannot use percent ionization values. Okay, there's a calculation that we can use here where we can say the percent ionization is based on the degree of ionization of the acid as it hits the water. So it's going to be the H3O plus concentration divided by the initial concentration of the acid. Now for strong acids, it's going to be 100% ionized. So in this case, it's always going to be H3O plus equals the initial concentration of the acid. Now I'm calling any acid here HA. For any acid, right? So this is going to be the initial concentration of any acid that we're dealing with. So here we go. And we can rearrange this equation to say that, all right, if I want to get the H3O plus, then it's simply going to be the percent ionization or percent reaction times the initial concentration. And the 100 here is simply to get rid of the percent sign. So let's look at a couple calculations here that involve percent reaction or percent ionization. All right, we want to be able to calculate the pH of a 0.1 molar solution of methanoic acid. Now we know methanoic acid is a weak acid. It's less than 100% ionized. You can check your table for that. And because it's a 0.1 mole per liter initial solution, that we can use our percent reaction for this particular question. So here we go. Here's the ionization reaction for methanoic acid. And we can get our value from the table. It's 4.1% reaction, so very weak acid indeed. And if we want to calculate the pH of this, then we simply want to figure out the H3O plus. So we can figure out H3O plus by saying it's the percent ionization times the initial concentration of our acid. And the initial concentration of the acid was given to be 0.1. So here we go. We plug in the values here. And what do we get? Okay, so it's 4.1 divided by 100 to get rid of the percent sign times 0.1. And we end up getting 0.004 moles per liter. Or we can change that to scientific notation, 4.1 times 10 to the minus 3. So now I want to get the pH of this, so I want to do the minus log. And remember we said we can estimate what the pH should be. It should be anywhere 1 less than that exponent. So the pH is going to be somewhere between 2 and 3. So when we do our pH calculation, minus log of the H3O plus, lo and behold, we get 2.39. Okay, now make sure you can do this on your calculator, the pH thing, and again look at the value 2.39. That's what we estimated it to be, between 2 and 3. So we got a good idea of where we're going. Okay, in this case we want to find the percent ionization, and what we're looking at is we're saying that the concentration of boric acid this time is 0.15. Now, you might say, well, why can't we just go to the table and look at the value on the table for boric acid? Well, we can't do that because the table values are based on 0.1 mole per liter. So we have to go about figuring out the concentration the percent ionization by doing a calculation. So here's the ionization reaction for boric acid. It's a weak acid, so it only partially ionizes. What's given to us is the initial concentration of the acid and the pH. So now that we know the pH, we can easily find the hydronium concentration by doing the calculation. H3O plus is equal to 10 to the minus pH, so we say 10 to the minus 5. So therefore we can get our hydronium ion concentration, 1 times 10 to the minus 5 moles per liter. Now that we have the hydronium and the initial, getting the percent reaction, it's simply saying, well, this went forward this amount. So let's calculate the percent reaction. And we're saying then that the percent reaction is the amount of H3O plus that we get divided by what we started with, the initial concentration, times 100%. And lo and behold, we get 1 times 10 to the minus 5 divided by 0.15, we get 0.00667%. That's not very much. And we can say, well, you know, this doesn't match the table value. If you look at the table value for boric acid is 0.0076. We're very close, aren't we? But the table value was based on an initial concentration of 0.1 mole per liter. And that's why it's slightly different, because our initial concentration was 0.15. So that's why we couldn't use the table value. So it's very close. So again, you can look at it and give it an idea of, you know, am I in the right ballpark? And yes, we are. We're a little bit different simply because we had a different initial concentration. There we go. Okay, in this case now we want to get into equilibrium expressions Ka, because we're going to be dealing with more situations that the initial concentration is not 0.1. So using the percent ionization calculations are very limited. We want to be able to calculate it for any concentration that we're given. So in this case, we're going to have to use Kas and Kbs from the acid-base table. And sometimes if they're not on the acid-base table, then we would give you the value of Ka or Kb, or sometimes you may need to calculate it. So here we go. This particular question says a cleaning solution is prepared by dissolving ammonia in water. The equilibrium concentrations of ammonia and hydroxide were found to be 0.35 and 0.25 respectively. Now respectively simply means in the order in which they were given. Now in this particular question, they're telling us that we have equilibrium concentrations. So no ice table is necessary in this case because we already know the equilibrium values. Okay? Now in this particular case, we're saying it's the reaction of ammonia with water to produce ammonium ions and hydroxide ions. They're telling us the concentration of the hydroxides at equilibrium. All right, they're telling us the concentration of ammonia at equilibrium, and we're simply looking at this and saying, hey, this is a 1-to-1 ratio. So because for every 1 hydroxide we get, we had to get an ammonia to come along with it. So the concentration is going to be the same here. So what we have are equilibrium values for every single one of these guys. I don't have to worry about water, because remember, water is a liquid. It's not included in equilibrium, so ignore it. So we can easily calculate K here now because K is based on equilibrium values. So we can say, well, this is going to be a Kb because it's ammonia acting as a base. And we simply plug in our equilibrium values. And we plug in these values that we found up on top here. And we figure out that Kb is going to be 1.79 times 10 to the minus 5. Now this value, 10 to the minus 5, is much less than 1, which tells me the equilibrium favors the reactants. So this is a weak base. In other words, ammonia really doesn't want to react with water. It would prefer to stay in NH3 form, and it doesn't want to do a whole lot of this. It does a little bit of it, but not a lot. And that's what this is saying. It's a very weak base. It doesn't want to break down, or it doesn't want to gain any hydrogens. Okay, some variations to this question. Okay, instead of me giving you the concentration of OH, I could actually give you a pH or a POH, and then you'd have to calculate the hydroxide ion concentrations. Because remember, we could do things like this. Don't forget what you already know, right? pH plus POH equals 14. And we could also get the hydronium and hydroxide by using this formula, right? Kw is hydronium times hydroxide. So I could do variations of this question by giving you a pH, and then you have to find pOH and then calculate the OH minus, or you could do the opposite there. All right, so there's lots of variations that we could do of this particular question. Okay, here's another one, calculation of hydronium or hydroxide using K this time. So this time I'm going to give you a K value, and I want you to find the concentration of the hydronium or hydroxide ion. So in this case, I'm giving you some propanoic acid. It has a Ka of 1.3 times 10 to the minus 5. It has an equilibrium concentration of 0.050. We want to calculate the hydronium ions and the pH at equilibrium. So this is a bit of a tough question. Anytime a pH is given, it's assuming that the equilibrium has been attained. All right, we're at a state of balance, and when we measure the pH using a pH meter, that we're at a state of equilibrium. So anytime they give us a pH, we're going to assume we're at equilibrium. Or anytime they want us to find the pH, we're going to assume that we want to get the hydronium ion concentration at equilibrium or the hydroxide ion concentration at equilibrium. So when we measure pH, we're assuming the reaction has been, equilibrium has been attained. Okay, so in this particular example, what we're looking for is the pH of this solution. So I want to get the hydronium ion concentration at equilibrium. So here we go. You'll see what I'm talking about now in a second. Here's propanoic acid. Don't worry about that. We generally give you the formulas on the test. Here's propanoic acid, but you should know that from Chemistry 2202, right? So propanoic acid, here's the acidic hydrogen here. It's going to donate that to the water to produce propanate and some H3O+. So what we have here now is a situation where we want to set up, okay, just a little point note here. You notice how I've been referring to HA as any acid? So rather than write out this entire propanoic acid formula, I'm simply going to simplify this and say HA, where the A represents this ion, right? And the HA is simply representing this hydrogen that's been stuck onto this ion here. So HA is representing any acid. So it's the exact same chemical reaction that we're showing. We're only interested in the transfer of the hydrogen, so we can write it that way. So it's just a quick way of writing it and being able to shorten things up a little bit. So here we go. We know the equilibrium concentration of the acid because that was given to us. It says the equilibrium concentration of the propanoic acid was 0.050. Okay, so we write that in as equilibrium there, and we want to find the pH of this. So I really want H3O+ at equilibrium. Now, the idea behind this is that, again, it's a 1-to-1 ratio. So if I get one hydronium ion, I'm going to get one anion here. So we're saying that if this value is going to be X, then this value is going to be X as well. So what we simply do here now is we write our equilibrium expression. Ka is products over reactants. We put our values in, and we notice here now that we've got a situation where the Ka was given to us up above. Okay, I'm just going to draw a little red box around it. Ka was given to us, so I know that value. I don't know A minus and H3O+, that's X and X, but I do know the initial concentration or the equilibrium concentration of HA. So I'm simply going to do this calculation here, cross multiply X squared equals 6.5 times 10 to the minus 7. Now I'm going to take the square root of that, and it works out to be 8.06 times 10 to the minus 4 moles per liter. Now, again, estimate what the pH is going to be here. This is hydronium, so the pH should be somewhere between 3 and 4. We do our calculation. pH is minus log of the H3O+, and lo and behold, it works out to be 3.09. Okay? And again, I can't stress enough that whenever we do an equilibrium, all of these values here are equilibrium values in the K expression, right? Because that's the point at which equilibrium has been attained. and that's the values we want to calculate. So there we go. So double check your calculators here. Make sure you can get the numbers I get. You can pause the screen, of course. Check your calculators. Make sure you get these numbers. I wouldn't want to lose marks because I don't know how to use my calculator. Okay, we're going to look at some ice tables here now. So this is going to be a quick review of what we did in the equilibrium section. Some ice tables, and these pertain to acids and bases as well. And we're looking at this guy and we're saying a nitrous acid solution has an initial concentration. Here we go. Here's the terminology. Ice table, remember, initial change equilibrium. So it has an initial concentration of 0.25, and it says at equilibrium the hydronium concentration is 0.013. So we have to set up an ice table here because we got two different states. We got the initial state for one species, and now we got the equilibrium state for another one. So we have to do up an ice table here. And we're looking at this and we're saying, okay, nitrous acid, it's going to simply donate its hydrogen there to the water, and we're going to produce nitrite and H3O+. Now, this is the initial concentration of the nitrous acid. It was given to me. They didn't give me any of this. They didn't give me any of that. So 0 and 0. They told me that the equilibrium concentration of the hydronium was 0.013. That's that value right there. Okay? Now, we have to be able to fill out this ice table, and we're just going to look at this and say, okay, if we started with 0 hydronium, and this is what we ended up with, well, that's how much we went up by. So the hydronium went up by that amount, 0.013. And again, this is going to be a 1-to-1 ratio, so if I get one of these, I have to get one of these along with it. So if I get 0.013 hydronium, that means I've got 0.013 nitrate. There we go. We now know the equilibrium value of nitrate. It's 0.013. And likewise, this reaction is going to go this way a little tiny bit. So if I'm going to get one of these and one of these, that means one of these have to break down. So likewise, if I'm going to produce 0.013 here, that means I have to use up that amount right here. So the nitrous acid is going to go down by 0.013. And now I know the equilibrium value there. I simply subtract it. You notice I haven't been talking about water, right? I leave that out because you guys know water is a liquid. It's not included in equilibrium. It's a pure liquid. Now that I have my equilibrium values, I can proceed now to calculate the Ka. And here we go. Ka is products over reactants omitting water. These values are all based on the equilibrium values. So I plug in my equilibrium values, and lo and behold, I get a K of 7.1 times 10 to the minus 4. And if I'm going to look at these numbers and try to make sense of what this means to me, this is much less than 1. This is going to be 0.000713. That's much less than 1, which means nitrous acid is a weak acid. The reactants are favored. It doesn't really want to break down. Do these numbers make sense to us? They sure do. You know, at equilibrium, this guy is 0.23. This guy is only 0.01. You know, there's 20 times as much nitrous acid remaining. Not very much of this broke down. In fact, only a little tiny amount broke down, and that's reflective in this idea that this equilibrium really wants to go in that direction. These guys are favored. Right? The reactants are favored, and that's what this is telling me. Okay. And once again, in this particular question, they gave us the equilibrium concentration here. I could easily get this if they gave me a pH or a POH, right? I could work it out and say if they gave me a POH, then I could find H3O+ at equilibrium because it's going to be 10 to the minus pH, assuming that the pH is given at equilibrium as well. So, you know, there's variations that we could do on this question. Okay, there we go. Let's try another one. Okay, in this particular question it says an aqueous methanoic acid solution has an initial concentration of 0.75. There we go, an initial's given. And the pH of the solution is at equilibrium is 1.95. We want to calculate the Ka of this solution. So this is one of those problems. And here we go. This is methanoic acid. It's going to ionize, and the acidic hydrogen, remember, is from the carboxylic acid portion right here. So that's the hydrogen that gets donated. We have an initial concentration given, we have a pH, and we know that when a pH is given, that's going to be the equilibrium value of the H3O+. So because they gave me the pH here now I know that it's 0.01122 at equilibrium. All right, we've got our ice table set up again. Once again, we started with none of this stuff. The only thing that was put in this test tube, it says, was 0.75 molar methanoic acid. So if this guy goes up by 0.012, we started with nothing, then the HCOO- goes up by 0.0122, which means now we know the HCOO- concentration is 0.01122. And likewise, we know that this reaction had to push forward initially, right? Initially a little bit of it's going to break down because we got some here. So if this guy is all the 1-to-1 ratio, these guys all went up by 0.0122, this guy has to go down by that value, right there. And therefore now we know the concentration. Now let's have a look at it. We have to calculate a Ka for this reaction. Didn't break down very much, did it? It started with 0.75. It's ending up at equilibrium with 0.74. So not very much of this stuff really ionized, did it? So I'm going to predict that this reaction favors the reactants. I'm going to predict a Ka of much less than 1. Right? Because this did not want to break down. This preferred to stay in this form right here. It doesn't want to ionize. So let's go calculate it. Once again, we've got the equilibrium values. That's what Ka is based on, products over reactants. And once again, we omitted water because it's a pure liquid. We put our values in, products over reactants, work it out. And again, 1.7 times 10 to the minus 4. Is that what we predicted? We did. We sure did. We expected it to be less than 1. So in this case, Ka is much less than 1. And remember, the reactants are favored. That's what we predicted. Now this value is for methanoic acid is listed on the acid-base table. And if you go check it out, that it's slightly different than what we just calculated. Now the problem with that is, remember that K is dependent on temperature. And the table values are all based on the assumption that every measurement is made at 25 degrees Celsius. And any variation in what we would calculate for K would be a variation due to the fact that maybe we're not doing our measurements at 25 degrees Celsius. So any other temperature would give us a slight variation in the K value. So we should be pretty darn close, but it's going to be slightly off because we may not be at 25 degrees Celsius for this reason right here, right? Because K is temperature dependent. K will fluctuate if the temperature fluctuates. Here we go. Okay, here's another question. Lots of samples here. It's saying an aqueous solution, 0.5 molar sodium sulfite is prepared. The pH at equilibrium is 10.45. Ooh, that's a base. 10.45, it's greater than 7. We want to calculate Kb for the sulfite ion. So here we go. Now again, just like Bronsted-Lowry equations, sodium sulfite is ionic. It's going to be 100% dissociated. We're going to get sodium ions and sulfite ions. Sodium is going to be a spectator, so we're going to get something that looks like this. The sulfite ion is going to act as the base. The water is going to act as the acid. So we're going to get a transfer that way. And lo and behold, this guy is a base, and we see the OH-. So now we can say, yeah, okay, we can see where that Kb is going to come from here now. All right. We want to set up our ice table because they gave us an initial concentration of sodium sulfite, and they gave us a pH. Now, with this particular problem, again, pH is at equilibrium. So I have to show you where I got that value from, right here. We're saying that the pH is 10.45, so I want to get POH, which works out to be 3.55. And then from POH, I can calculate my equilibrium value of hydroxide, assuming that POH was measured at equilibrium from this one right here. And therefore, I can get now my equilibrium concentration of OH-. Okay? So they gave us an initial concentration of sulfite. We could figure out the equilibrium value of hydroxide by doing these two calculations below. And lo and behold, now we can start filling out our ice table. The OH minus must have went up by 0.002. That means the sulfite, hydrogen sulfite, went up by 0.00281 as well, which means now we know our equilibrium value of HSO3. These guys both went up by 0.0002, which means the sulfite must have went down by 0.0022818. It's not very much, is it, when you compare it to what we started with? So again, we're going to make the prediction here that, hey, this guy really didn't change much, did it? If we round that up to two significant digits, it's going to be 0.50. So in terms of being able to act as a base, the sulfite ion really is not that strong. It would prefer to stay as SO32-. It really doesn't want to go forward. It doesn't want to do it, right? Because this value is so tiny. And therefore, SO32- is going to be a very, very weak base. And you notice we've omitted water again because water is a pure liquid. Okay, so here we go. So we can start calculating here now the Kb. Since this is a base, right, we have OH- on the top, products over reactants. And now we can plug in our values, and lo and behold, when we plug our values in, what we notice here is that, right, products over reactants, 1.59 times 10 to the minus 7. That's very tiny. Very tiny value. And that's what we predicted, wasn't it? We predicted Kb to be much, much, much less than 1. Therefore, it's a very weak base. It prefers to stay as it is, right? No big change there. Okay, again, check your calculations on this. Pause the screen if you want to check your calculations to make sure you get what I get. And if you can't get what I get, then it might be a good opportunity now to see a tutor or drop me a line through the discussion postings. Or check with your teacher on site, your math teacher or your chemistry teacher, and they can help you out. Okay, here's another one, and this one's going to be another level of difficulty, I guess. In this case here, we want to calculate the pH this time of a sample of vinegar that has 0.83 mole per liter initial concentration. Now, vinegar, of course, you won't find it on the table as vinegar. And you guys would have to know that vinegar is really acetic acid, and that's found on the table as ethanoic acid. So what we're looking at here is that this vinegar is ethanoic acid, CH3COOH. And on the chart, we can figure out the K value of this. It's 1.8 times 10 to the minus 5. So we want to calculate the pH of this solution. Now, on the public exam, this question is going to be worth probably 3 or 4 marks. And I know what some people are going to do. Some people are simply going to look at this and say, oh, I got a concentration. Take the log of that. You're in money. Bang. But do you honestly think that they're going to give you 3 marks for doing one simple little tiny pH calculation? You know, punch one number in your calculator and you get an answer. You're going to get 3 marks for that? You want 3 marks on the public exam? You got to do at least 3 different things. You got to do 3 calculations or 3 steps. So here we go. In this case, we're looking for the pH, so we're looking for the hydronium ion concentration at equilibrium. All right, so obviously now you've got an initial concentration of the vinegar. You're looking for an equilibrium value. Right off the bat, you should be thinking, okay, ice table, initial equilibrium. So here we go. Here's the equilibrium expression, acetic acid. And remember, the acidic hydrogen is the one on the carboxylic acid group, right there. Okay, and as we go through, we're saying, all right, here's our ice table, initial, oops. Got to cover that up. That's too soon. Premature uncovering there. Okay, here we go. All right, we're looking at this particular setup, and we're saying, okay, the initial concentration of the vinegar was given, and we're looking for the hydronium ion concentration at equilibrium. I don't know what it is. I need to find it. If I can find that value there at equilibrium, then calculating pH, easy. All right. That's all we're given. We're not given anything else. So how do we go about this problem? Well, this is going to be one of those problems with unknowns. We started with nothing. We ended up with X. So in this case, we must have went up by X. The acetate ion started with nothing. And because it's a 1-to-1 ratio here, this guy must have went up by X as well. So now we know the acetate ion concentration at equilibrium. It's X. Now if the vinegar broke down to produce X amount of acetate and X amount of hydronium, then it must have went down 1-to-1 ratio by X itself. So at equilibrium, it's going to be 0.83 minus X. All right. We know how to take care of that X, don't we? We're going to make a simplifying assumption here. So we're going to try and make this problem as easy as we can. And we're going to do our 500 times rule. Recall that from the equilibrium calculations we've done on a few lessons back. Our simplifying assumption is going to state something like we take the initial concentration of the acid. Okay, that should be initial there. There we go. The initial concentration of the acid divided by its Ka value. And we got Ka even though it wasn't given to us. We could get the Ka from the chart. So we're going to divide the initial concentration by Ka. And lo and behold, this works out to be 46,111. Okay? Now, our assumption is, if that's greater than 500, we can assume that X is insignificant. And we talked about that before. So this is greater than 500. So compared to 0.83, the X is not going to make a difference. When I subtract the value of X and I round up, let me just look back here. Remember when I subtracted this value right here? Didn't make any difference, did it? So we could assume then that for sulfite ion, this change was pretty much insignificant. Didn't make any difference. So that's what we're saying here. We're saying, yeah, because the K value is so tiny, it's not really going to want to move forward that much. So any change that occurs here is pretty much going to be insignificant compared to the 0.83. So I'm going to look at this and say, all right, if it's going to be insignificant, let's just cross it out. It's not going to make a difference. Let's get rid of it. All right. Now that we've gotten rid of it, now we can make a nice easy calculation, because Ka, products over reactants, we omit water, plug in our values, and now we look at this and say, sure, that's easy now. X on top, X times X is X squared, cross multiply, and we get X equals 1.49 times 10 to the minus 5. Take the square root of that, and lo and behold, we get 3.86 times 10 to the minus 3. All right, we're still not finished, because this question wants us to calculate the pH. Now we know that X is representing the hydronium concentration. So because the concentration is 3.86 times 10 to the minus 3, I'm going to predict the pH between 2 and 3. pH between 2 and 3. We do our calculation. pH is minus log of H3O+. And lo and behold, we get 2.41 as predicted. And there we go. Now, is our assumption correct? I always like to verify to make sure that, yeah, we did the right thing here by crossing out the X. And I'm just going to show you the calculation quick. So what I'm going to do here is check my assumption, say, okay, 0.83 minus X. I put my value that I just found for X here, 0.00386. I do the subtraction. And because we got 2 digits of significance, the 6 is really going to round up, isn't it? And in a sense, after I do my significant digit business, that the value of X, the change, really made no difference. So our assumption is valid. It's good. It's a good assumption. It's not going to make much difference at all to the pH. There we go. Now, how did I get public exam question 3 marks? Well, if you look at this, they're going to give you 1 mark for your ice table. Easy marks. Should do it. Don't forget to write it in. If you forget to write your ice table down, they will definitely dock you a mark. You'll get 1 mark for your simplifying assumption. You'll get 1 mark for showing me the Ka expression and working out the numbers, and they'll probably give you 1 mark for calculating pH. So this question on the public exam could potentially be worth 4 marks. So do you think that if you looked at this question and you simply took the log of that they would give you 4 marks? A lot of work, isn't it? You're going to work for your marks. If a question is worth 4 marks or 3 marks, generally you have to do 3 or 4 things. Okay, here we go. Okay, more on the simplifying assumption, to quad or not to quad. I'm going to have to show you guys how to do a quadratic here, because sometimes they show up on the public exam. So let me just show you a couple here. And again, just to quickly review the quadratic, the 500 times rule, this is what we just did over here. We're saying, okay, if the initial concentration over the Ka value is greater than 500, X is insignificant. Cross it out. This change that's represented here is insignificant. So in other words, the equilibrium concentration of the acid is basically what the initial concentration of the acid was, because the change is insignificant. However, if you do your simplifying assumption and you find out that the simplifying assumption is less than 500, then what that's saying is the change is significant. There's the amount of X that's changing is going to make a big difference to the equilibrium value. And because it's making a big difference, now it's going to influence the pH significantly, because the amount of H3O plus is going to be much larger than we expected it to be. All right, so in this case, we would have to use what's called the quadratic equation. And I'm assuming that you guys have already done the quadratic equation in math and whatnot, and you've seen it before, and you know how it works, and you know that it's minus b plus the minus square root b squared over 4ac times 2, or divided by 2a. The quadratic formula is actually found on your table of constants and formulas. All right, the public exam includes it with their formula sheet, so you never have to memorize it, but make sure that if you need it, you know where to find it. It's on that answer on the formula sheet. So let's have a look at one of these that requires the quadratic. All right, here's a very similar example to what we just did there with the acetic acid. In this case, we're going to use some hydrofluoric acid, and the initial concentration is 0.01. All right, so we start doing this particular problem, and we say, okay, it's going to be the ionization of HF with water, and the value for Ka we could get from the table. Works out to be 6.6 times 10 to the minus 4 from the table. All right, so those values are available to us. We're looking at an ice table situation here, whereby the initial concentration is given of the hydrofluoric acid, but nothing else. So we're saying we want to get the pH. So we want to get the pH here. So we want to figure out the H3O plus concentration at equilibrium. Once again, we know that we went up by X. The fluoride ion went up by X, so we know that the concentration of these two at equilibrium are the same. The hydrofluoric acid must have went down by X, so therefore the equilibrium concentration of HF is 0.01 minus X. Okay, now here's where we start to get into this. We start doing the 500 times rule. So again, on the public exam, they will give you 1 mark for doing the ice table. Easy marks. Do it. Show us. You get a mark for that. The next thing you're going to do is state the 500 times rule, or the simplifying assumption. And when we state this, they want you to write it out. All right, so it's going to be the initial concentration of the HF divided by its Ka that we found from the table. And when we do this calculation, we find out that, oh no, it's only 15. And 15 is much less than 500, which says, okay, boys, this is going to make a big difference. Whatever this value is for X, when we subtract it here, this is going to be substantially less than what we started with. So it will make a big difference. So it's going to be large enough to make a difference. So we're going to have to do the quadratic equation. So let's have a look at how this works. Now we still proceed the same way. Oh, by the way, this will get you another mark. That's 2 marks out of 4 or 5. Easy marks, right? Everyone can do that. What we have to do now is state our equilibrium expression. Believe it or not, they'll probably give you another mark if you do that. Products over reactants. We start plugging in our values, and this is where it starts to get yucky. Okay? It starts to get yucky here. I don't know if I can use that word yucky, but in any case, when you cross multiply here, you're going to multiply 6.6 times 10 to the minus 4 right here to get that, and then you're going to multiply it here by minus X, and you're going to be left with X squared on top. So when we do this and simplify it, okay, this is what we end up with. So 6.6 times 10 to the minus 4 times 0.01, 6.6 times 10 to the minus 6, minus 6.6 times 10 to the minus 4 times X. And this is equal to X squared on top. What we're going to do is put this in standard form for a quadratic. We're going to put it equal to 0. All right, so I'm going to bring my everything's over. All right, so these guys, this one's going to be pulled over to this side. this one's going to be pulled over to this side, and it's going to equal 0. Don't forget to change the sign when you bring it to the opposite side. So what we end up with is an equation in standard form for a quadratic. And once you have it in standard form, we can see that the A value is 1. The B value, the one that goes along with the single x here, is going to be 6.6 times 10 to the minus 4. And the C value is going to be a negative 6.6 times negative 6. All right, now that you have your A, B, C values, I'm not going to do the calculation here. What you guys have to do is plug those into the quadratic equation. You get two values for x because of this plus or minus right here. Now, you know you can't have a negative concentration. There's no sense. And once you get 0, you can't have any less than 0 when it comes to concentration. So you're always going to take the positive value for x. And what you end up with is a concentration of 0.0226. So when you do this and put these values in your quadratic, this is what you should end up for your positive value. So give it a try and make sure you can get the answer that I have there. And now that we have the value for x, we can easily get the pH. That's 2.26 times 10 to the minus 3. So I'm expecting a pH somewhere around 2 or 3. And there we go, it's 2.65. So quadratic equation, this question on the public exam, there you go, another one for solving this. And one for doing your quadratic, they give you credit for that, and then one for your pH. So this question on the public exam would be worth 4 or 5 marks. So a lot of work, and that's why it's worth so many marks. Okay, so this one's a good one to model your work after there, I guess, in order to try and do these quadratics. Okay, one more example before we go. I know this lesson is dragging on, but this one showed up on a public exam from a few years back, and it was worth 5 marks. 5 marks. Okay, in this particular question, they want you to figure out the pH of an aspirin solution. The initial concentration is 0.022. They gave you the Ka value. We want to figure out the pH of this solution. All right, now this whole thing over here I'm going to refer to as HA. I don't want to be rewriting all that. All I know is that there's one hydrogen that's going to be donatable, so I'm going to represent that as HA. The A represents this anion. Okay, so here we go. We write the expression for aspirin. HA is, all right, so this guy's going to donate its hydrogen there to produce that. We know the initial concentration. We know we're looking for the equilibrium. So we know we're looking for H3O plus at equilibrium. So the same thing as the last problem. That one goes up by x, which means the A minus goes up by x as well. So we know that the concentrations of these two would be the same. Both of them are going to be x. And the concentration of the aspirin is going to go down by x. And we're looking at this and saying, okay, how big is that x? Is it going to be significant? Is that going to make any difference there? Can we cross it out? If we can cross it out, that's wonderful. The question's easy. If not, then we have to do the quad. The only way we can determine if we have to do the quadratic equation is by doing our simplifying assumption. The initial concentration divided by Ka. There we go. You work it out. The answer you get is 66. Oh no. 66 is less than 500, which means x is going to make a big difference here. It's going to be significant when it is taken into account. So because it's significant, now we have to do the quadratic formula. And here we go. We write our equilibrium expression for our mark. We plug in our values. Okay, there we go. Once again, you notice all these x's flying around here. Now we have to start cross multiplying. So 3.3 times 10 to the minus 4 times 0.022. And then 3.3 times 10 to the minus 4 times minus x. And that's going to equal x squared, like that. Now we have to throw these guys to the other side because we want it to equal 0. And don't forget to change your sign of these guys when you flip them to the other side. And lo and behold, what do we get? 0 equals x squared plus 3.3 times 10 to the minus 4 times x minus 7.26. So we've got our A value, we've got our B value, and we got our C value. That's an equal sign there, by the way. So we got our C value. It's a negative 7.26 times 10 to the minus 6. Now that we have our A, B, C values, we proceed to do our quadratic. and again, you can put the values in and see if you get the positive value that I get. Okay, there we go. It's 0.0253, and that's 2.5 times 10 to the minus 3, so I'm expecting a pH somewhere between 2 and 3. And there we go, 2.6. All right, so once again, 1 mark for the ice table, 1 mark for the simplifying assumption, 1 mark for Ka, another mark for showing me that you can solve the quadratic formula and all that, and another mark for the pH. Now, if you don't get the right answer, does that mean you lose all 5 marks? Absolutely not. On public exams, they check and correct things for process. They want to see that you're doing the right sequence of steps. You know what you're doing. If you just messed up on, say, even this part, if you messed up but you continued to do your quadratic and stuff, you'd still would have got 1, 2, 3 marks, even though you messed up the last 2 steps. And they would probably give you something for effort and whatnot here as well, you know, knowing that you did this calculation correct and stuff like that. So don't give up on these questions. Make sure you go and give them a try. Now I had something here too. This is the last question, and I did a little assumption check here. Remember we said that x was going to be significant? I just want to do that check right here, and I'm showing it right here. So this is 0.01 minus x. So I got 0.01 minus the x value, and you notice that, yeah, it made a big difference, didn't it? You know, it's gone down by almost 30% here. So it went from 0.01 to 0.007. So it did drop significantly, and that's why we had to do the quadratic. There we go. Okay, give some of these a try. There's lots of these in your textbook, lots of them on the old public exams. Go get a public exam and check it out and see what type of question is there. Don't forget, utilize our free online tutoring. A lot of online materials here. We have 4 public exams where a teacher has actually sat down and worked out real-time live as a recording how to do the public exam questions. So go check that out, and that link of course is on the CDLI homepage under content. So go have a look. Bye-bye.